look at polynomials part 1. So just so you know, this is a much larger unit, okay? It is a very heavy algebraic unit. So there's going to be lots of this solving for x type stuff. Okay, so today we're going to break down some of the terminology in there so that you're aware of the vocabulary. Some of this you've seen, like the term variable you've seen. We talked about that back in our powers unit. Topic. I didn't fill that in. But in general, it gets heavy quick, okay? For those students who are thinking of doing the pre-cal math next year and the applied math in years to come, this will definitely increase in terms of how much algebra you do. For those doing the other math, the consumer math, as we get into that one over the 4 years, then algebra will not be as big a component. Okay, it'll still be there, but it'll be less of a component in those math courses. But this is part of your grade 9 curriculum, so I want to make sure I get through that with you. For some students, I realize that algebra is something you struggle with. So I'm going to try in this unit to provide you guys with kind of recipes for solutions. Okay? So in some cases, you may not fully understand what's going on, but if you follow the recipe, you'll get to the answer. And that's good, right? That gives you points on things like tests. Okay? So for some of you, that's the case. For others who are going to go further with this, I want to try and make sure you understand sort of all the components and the sort of future potential of some of this algebra. Okay. Turn that on. Okay, so here's what the actual curriculum says. And again, we're not going to read the whole thing. But what it says is, oh, that's why it's not working. Okay, you need to demonstrate an understanding of polynomials limited to a degree of less than or equal to 2. And we'll talk about what those words mean. Okay? Boys, I've got more chairs I can separate. Please stop. Okay? You need to create a model or a pictorial view of it. You need to know what the word variable, term, coefficient, constant, and what a simplified expression is. You need to know what the degree of the polynomial is. So we're going to look at what those things mean today. Okay, so first some terms. Okay? Some of these will be a bit of a review from the powers unit. Okay? A letter that represents a number is called a variable. So in math, if you see letters, those are variables. A number that multiplies a variable is known as a coefficient. Okay? So for example, in 2y, y is the variable, 2 is the coefficient, because that means 2 times y. So a number that multiplies a variable is called a coefficient, and the letter is the variable. Okay. When you combine these things together, variables and numbers and stuff, we often have what's called an algebraic expression. Okay? So this is an expression. X plus 2y plus 10 is called an expression. Okay? In the expression, x plus 2y plus 10, we have 3 terms. Okay? So let's be clear about the difference. A term is part of the expression. Now here's, maybe it's just because I'm a fat guy, but this is the way I usually like to say it. If you think of the algebra as a cake, a big piece of cake, the terms are the pieces of cake. Okay? So you put the pieces together, you get the whole cake. So I put 10 together with 2y together with x. I have 3 pieces in this piece of cake. Now the reason I use the cake analogy is because I think that's a way you can use it to divide it up. Okay? And here's what I mean by that. Okay? Let's write an algebraic expression. So I'm going to use a variable, x. I'm going to use a number. Now, in algebra, when it's just a number by itself, we actually call it a constant. So I'm going to say plus 2. 2 is a constant, right? Doesn't change. Minus 2x. Now, 2x is a term. It has a coefficient. 2 is being multiplied by x. But actually, it's not 2. It's negative 2. Okay? But here's the whole cake analogy, the way I usually like to say it. If I think of this whole thing as the cake, okay, and I'm going to serve cake to people, I've got to cut it up into pieces. The way I cut it is in front of the signs. So here's a sign. That's a negative sign. So I can cut the cake in front of that sign. Here's a sign. I can cut it in front of there. If I don't see a sign, what can I assume it is? Like, what sign is X? No, but is it positive or negative? Right. Usually, if we don't put a positive, we assume it is. So this piece of cake, or sorry, pardon me, this cake has 1, 2, 3 pieces to it. Or it has 3 terms. This algebraic expression has 3 terms. Let me show you another one, okay, real quick. Okay? Negative 3x plus 2x minus 3 plus 4. Okay? We have this big piece, this big cake. Let's cut it up. Go in front of each sign. So there's a positive sign, cut it. Here's a sign, cut it. Here's a sign, cut it. There's a sign. How many pieces to the cake? 1, 2, 3, 4. How many terms in the expression? 4. There are 4 terms in this expression. Okay? So when I say the word term, okay, that's what I'm talking about. I'm talking about the terms in this expression. So now you look at this, you go, oh, 1, 2, 3 terms. Okay? Hopefully that is a recipe. It's all these food analogies. That makes sense. 10, as I said, when it's just a number, in algebra we call that a constant. Okay? X and Y are the variables. 2 is the coefficient, because 2 goes with Y. They're joined together through multiplication. Okay. Now, believe it or not, there is a coefficient for that X. There is a number multiplying X. We don't usually write it, but it's the number 1, right? 1 times X equals X. That can be a bit confusing. So if that didn't quite sink in, that's okay. Don't worry about that. In algebra, if they have the same variables, they're called like terms. So 2x and 3x are alike. Why? Because they both contain the same variable. Right? So they're both alike. 2ab and 3ab are alike. Now in this case we have 2 variables, but they both have the same 2 variables. Now here's a question. Is 2x like 2ab? No, they're not the same variables. If they don't have the same variables, we call them unlike. So they're alike or they're unalike or unlike. Okay? Now, it gets more complicated when you add things like exponents to it. So here I have 7x and 3x squared. Those are considered to be not alike. The exponent matters. So having an exponent there matters. It makes a difference. Okay? So let me go back to that example here. The one we were just doing. Here's the 4 pieces of cake. Right? 4 pieces. Are any of those pieces alike?
Yes.
Which ones? The first 2. These 2 pieces are alike. This one is like this one. What about these 2? Are they alike? Well, what are they? What would you call those? What would you call the number negative 3? No, not a coefficient. Close. It starts with a C. Constant, right. So this is also a constant, right? So they are alike. Now, forget the rest of this. If I just gave you this on a math test, negative 3 plus 4, you could probably solve that, right? It's 1, right. In other words, if I took those 2 pieces of cake that are alike and smushed them together, I could have 1 piece of cake. I sometimes do that with soap. You ever do that with soap when you have like these 2 little soaps? You try and squish them together and make 1 piece. Okay, never mind. Maybe that's just me. But wait a minute. Can I do that with this? Can I say I have negative 3x and positive 2x? If I squish them together, what do you think is going to come out?
You wouldn't be able to know because...
No, you actually can know. You can. What do you guess it could be? 1x, close, not quite right. Negative 1x, right. Let me try a different one. Let's try, those weren't very good numbers. Let me try this one. 5x minus 2 plus 3x plus 4. So you're given this algebraically. So you think to yourself, okay, let's cake it. Turn it into a cake, and let's start cutting it up. Cut up the 4 because there's a plus sign there. Cut up that. Cut up that. I have 4 pieces. So now I start looking for pieces that are alike. Is anything like this one? Wait. 3x. Let's be clear. This one and this one are alike. Anything else alike up here? Yeah. Okay, but let's use the right terms. Use the right words. What are negative 2 and positive 4? Constants. The 2 constants. This and this are alike. So let's take the 2 constants, this one and this one, and smush them together. What are we going to get? Positive 4, negative 2? Be clear. 2, positive 2. Okay? Now, let's think. We're going to smush 5 x's together with 3 x's. 8 x's. That's right. We're going to get 8 x's. And that is exactly what you can do. You can, what's called, combine them. Okay? We're going to see that more in a minute. Okay? So right now we've got these terms. Like terms, unlike terms. Okay. Now as well, some people like to do this visually. I myself am not a big fan of this, but some students are. And it is actually part of your curriculum. What they have, and maybe you had this in grade 7, maybe, or 8, is these things called algebra tiles. The algebra tiles are things that are drawn. Okay? Like I said, I'm not a big fan of them, but I would do a disservice not to show you what might possibly be on your exam. Here's the way they are drawn. Okay? They're drawn as either small squares or large rectangles. If it's a small filled-in square, and you can fill it in with basically any color you want, but if you're just using your pencil, it'd probably just be pencil-filled, that represents positive 1. If you draw it without filling it in, it represents negative 1. If you draw it as a rectangle and it's filled in, it represents positive x. And if you draw it as an unfilled rectangle, it represents negative x. Now, here's how, and they actually have these tiles. They're actual physical tiles that you can play around with. I don't have any in here. I do have some in the other room, which will be in next week. Okay? Here's how you use them. I'm just going to dim the lights down a bit. Austin, actually, you can be my light guy. Can you just flick that light down? The light switch, yes. Okay, here's how you use algebra tiles. Okay? I'm going to use them to create expressions. Now, you know what an expression is. It's a collection of terms. Here's an expression. Negative 2x. Okay, see what I have there? I have 2 unfilled rectangles. Each one is an x. So I have 2 of them. I have negative 2x. That's positive 3x. I have 3 of them, all filled in. They're all x's, so I have 3 x's. Let's get a little more complicated. This one is negative 9, because these are just 1s. So if you count them up, there's negative 9 of them. And here I have positive 6 x's. And finally, this one is negative 8x plus 3. Okay, so the tiles can be used visually, but let's see what I can do with them. Okay, I can make 0 out of tiles. Okay, and the way I do that is I have one tile cancel out the other tile. So for example, if I have a positive tile and a negative tile, they essentially create nothing when you put them together. So simply, let's just try a simple example. That's positive x and negative x. They join together to make 0. This one is called the x squared tile. Okay, it's a much larger rectangle, and I can combine those to create 0, or I can just combine 2 little guys to create 0. Or I can do all kinds of different combinations to create 0. For some of you, that might be confusing, so let's let that go by. Okay? So let's see how I could use algebra tiles to solve algebra problems. Okay? And to be honest, this is a bit of a look ahead. Let's not focus too much on this today. But let's see if you guys got this. Some of you might have. What's another way I could say this? Like, what does this mean? What does that tile mean? X, positive X. What do those tiles mean? Okay, count them. How many is there? So how would we say that? X plus 4 equals what? Negative 2. That's right. X plus 4 equals negative 2. What's the other one? What is it?
X minus 3
Equals?
negative 8.
X minus 3 equals negative 8. That's right. For some of you, this is a visual cue. Okay? For others, as I've said, I'm not a big fan, but it is something you should be aware of. Okay, now moving on. We ultimately have to figure out what x is. That's the point of algebra, is to figure out what this unknown value is. To do this, we need to always keep a balance. And the balancing point, you guys may remember this from elementary school on the teeter-totter. The place where it balances is the equal sign. So you can think of the equal sign as the center of a teeter-totter. And it always has to be balanced. So whatever you do to one side of the teeter-totter, you have to do to the other side to keep it balanced. Okay? In math, we sometimes like to call it the left-hand side or the right-hand side. I'm not too worried if that's the way you think of it. But let's see how this would apply to solving a problem. Here's an example. X minus 2 equals 6. So to solve this, if we think of the equal sign as the center of the teeter-totter, like this. So here's the teeter-totter. Everything on this side of the teeter-totter equals everything on this side. They're balanced. So if I'm going to do, like again, let's imagine you had like 5 kids sitting on this side of a teeter-totter and 1 fat kid sitting on this side of the teeter-totter. That's kind of cruel. Okay, let's not be that way. Let's go 5 kids and 10 smaller kids. If I have a bunch of kids jump off one side, all of a sudden the teeter-totter is going to go flying unless I balance it, right? That was awful. That was awful. All right. Here's how we balance it in math. We're going to get rid of that negative 2 by adding 2, right? Negative 2 plus positive 2 equals 0. Gets rid of it. But what I do to this side of the teeter-totter, I got to do to this side. So if I'm going to add 2 to this side, I've got to add 2 to that side. What you do to one side, you have to do to the other. Now, because these 2's are canceled out, I'm left with just x on one side. But on this side, I have to add 2 to the 6. So I'm going to get 8. And now it's done. It's balanced, and I've solved what x is. Because, I mean, some of you probably saw that right away. Something minus 2 equals 6. It was 8. But that's the process, is balancing both sides. Let's make it a little bit harder, okay? Well, we'll do it in a minute. All right. You are essentially creating 0 on one side to get rid of that 2. You're making it into a 0, okay? You're making it into a 0 so that your variable is left alone. Your variable wants to be left alone. What we call that is isolate it. We are isolating the variable, okay? You can do this with tiles too. Watch how I do this with tiles. So here's my x. It's not alone. It's got some other junk there. How would I get rid of it? Well, I got to make 0 out of those 4 tiles. So I put the opposite 4 tiles there. So in order to get rid of these 4 tiles, I put 4 negative tiles, essentially creating a 0. But what I do to one side, I got to do to the other. And now what I'm left with is that x equals negative 6. Because there's now negative 6 tiles over on this side. Again, for some of you, that might be a bit challenging. I'm not going to worry too much about the algebra tile stuff today. It's just something to think about. Okay, a couple more terms you need to know. Because this was in the curriculum at the beginning, this word. So you need to know what it means. A monomial is an expression with one term. Okay, 2x, that's a monomial. Mono means 1, right? Mono, the word, means 1. A binomial, like a bicycle, means 2. Bi means 2 terms. Trinomial, like a tricycle or a triangle, means 3. Yes, Simon?
Is it a bad thing that my teacher last year taught us that this is like the first one binomials or something like that?
No, that's a good thing. But the word polynomial, that's the one that seems a bit confusing. Like the word polygon means more than one. Okay? Poly means multiple. So a polygon or a polynomial means multiple. So here are monomials, right? These are one-term things. That's a binomial, two terms. This is a trinomial, but it's also a polynomial because there's more than one. Okay? So it's just words, fancy words that mathematicians are using. Don't be confused by them. Okay? Monomial 1, binomial 2, trinomial 3, polynomial more than one. Okay? You could, yeah, you could call it that. Okay. Now this is maybe even a little bit more confusing to some of you. Again, for some of you this might be pretty hard. For others, this is definitely something that would be more on the more challenging side. Okay. This relates now to the powers unit. The degree of a monomial is defined as the sum of its exponents of its variables. Here's an example. Okay, so that's a term. Okay, so it's a term with 3 variables, 1 coefficient, and there's a couple of exponents in there, right? Notice the exponent, which means x to the power of 3. What this really means is 2 times x times x times x times y times z. But to write that all out is a lot of work. So mathematicians came up with a lazy way to write it, and that's this way. But when I'm talking about the degree, what you do is you sum up or add up all the exponents. Now, this is kind of a trick question. Before I show you the answer, let's add them together. What's the exponent on the variable x? No, it's 3. What's the exponent on the variable y? 2. So what are we adding so far? What do we got? 3 plus 2.
5.
What's the exponent on the variable z?
1.
Right. Very good. Why is it not 0?
Oh,
Excellent. You guys remembered that. So 3 plus 2 plus 1 means that this thing has what's called a degree. It's kind of like a degree of difficulty. This has a degree of difficulty of 6. In other words, that's a hard type of algebra. It's 6 hard. Okay? This one, 4x to the power of 3, has only a degree of 3. Okay? This one is like the other one, has a degree of 6. Okay? Now, if your polynomial has multiple terms, like 6x squared plus 3x, you take the highest term. So what's the degree of 3x? Sum up the exponents of the variables. 3x. What's the only exponent we have? 1. So it has a degree of 1. But in 6x squared, the x has a degree of 2. So the highest term is the one that counts. So it's a degree of 2. With this one, I have x to the power of 5, 7x to the power of 2, and then negative 3, which has no variable whatsoever. But the highest term is a 5. Okay. Let's try another example. Okay. Notice in these much more complex ones. Okay. With this one, I have to sum those two. 3 plus 2 is 5. With this one, what's the degree of that one? 5, right? What's the degree of that one? 6, right? The 5 plus the 1 that's invisible is 6. So out of those 3, 6, 5, and 5, the highest one is the 6. Same with that one. Okay? Now, in a second, we're going to relate that back to the beginning. Okay? Here's that cake thing again. The like terms getting put together. Okay? Sometimes you have to assume something to be positive. So here's an example. This one I have no variables. Okay? But in this algebraic expression with no variables, I have a bunch of terms. I can, just like with a piece of cake, I can rearrange those terms. Like I can do this. I can put them in different orders, and I'm still going to get the same answer. We learned that back in a couple units ago in the order of operations, that I can change up the order here and I get the same, no matter what the order, I'm still going to get the same answer. Okay? As long as they're of that same order. Okay? I can do the same thing with variables. So in this one, I have A minus B plus C minus D. But I can change that, okay? And I'm still going to get the same thing. I can move them around, okay? So all these things are essentially meaning the same thing because the sign goes with it. So negative B, if you think of it like a piece of cake, I can move that piece of cake to the front. The sign goes with it. So what's the sign on the A? Positive, right? So that positive sign goes with it, okay? All right. This obviously can get more complex. Algebra tends to do that. So with this one, as a giant piece of cake, if I cut it up into pieces, I can rearrange the pieces. I can squish two of them together, and I can squish these two together and make it a simpler two-piece of cake rather than a four-piece cake. Okay. I think we'll wrap up there. We'll leave the examples for Wednesday, not Tuesday, because